Jessica Lovering is going to talk to us next a little bit about the upfront cost of nuclear, which we were just discussing, and how we might be able to radically reduce that. And Jessica is with the Breakthrough Institute and is the director of the energy program at that organization.
All right, thank you, Ryan, and thank you for the host for inviting me to speak. I'm very passionate about this topic, and I hope to answer lots of questions later on. I am going to focus on cost, but I have a lot of background knowledge on sort of all issues around nuclear. That's my main focus of study, so welcome any question. But Armin went through a lot of the reasons why we need nuclear, particularly for its reliability and its stable costs. I just wanted to add really quick that nuclear is the U.S.'s largest source of clean energy. It's also Europe's largest source of clean energy. And it's also, from history, the fastest clean energy source to scale up in terms of how much clean energy you could add per year. So those are really important from an environmental perspective if you're looking at how do we build a lot of clean energy really fast. So when I talk to people, mostly I talk to environmentalists who are concerned about climate change, and when I talk to them about the problem of climate change and pollution, I'm really surprised that the question about nuclear that they usually have is about the cost. Especially the high upfront cost seems to be insurmountable and take too much effort if we're really trying to solve climate change very rapidly. So that's what I'm going to dig into today and really focus on, is how much of a burden is that cost, and is there a way to bring that cost down a lot? So let's think about the historic costs of nuclear power. So when you think about this, whether you realize it or not, you've probably got this chart in your head. Well, you at least have this story in your head about nuclear costs. So what I'm showing on the y-axis is the construction cost of a nuclear power plant, that upfront cost. And the x-axis is time. So this is the whole history of nuclear construction in the US and France. The US is blue. So the US is the story most people think of. It started off very cheap, cheaper than coal in a lot of places, and utilities really wanted to build it, and then it rapidly grew in costs. Tripled, quadrupled in cost through the 70s and 80s. And that's really for one of the reasons we stopped building plants, and we haven't been building plants for the last 30 years. We did bring the first plant online last year in 30 years. Now contrast that with the experience of France. Is very different. France started a little bit after the US with their big commercial program, but they started a little bit more expensive than the US, but maintained very low and just gradually increasing costs. And they did that through reactor standardization, building a lot of reactors at the same site, and having a very centralized control over regulation and industrial policy. So these are very different experiences. But that's only a very small part of the story, because there are 31 other countries that have commercial nuclear power. And for a long time, we didn't really know what the cost history was in those countries. But we did a big study to try and dig those up. So we found costs for 7 countries total for the whole history of their nuclear program. That's what I'm going to show here. So this is a bigger picture. And I'm not going to go into all these details, but you can see that there's a lot of different stories in here and a lot of different trends in nuclear costs. But just to highlight some of the main ones, we can see that in the early history of commercial nuclear power, costs fell a lot. And this was through innovation, through R&D, and also through economies of scale, building bigger reactors. And then there's a low point. This is when the big commercial programs take off, and you can see that countries go in a lot of different directions. We have Japan. It's kind of in the middle between the US and France. There's India, there's West Germany. I won't go into those. But the big story here, the one that's the most interesting, is South Korea, and that's the purple color. So South Korea started by importing French, Canadian, and US designs, and then they established their own domestic reactor, which was standardized, and they built a lot of them. They built a lot of them at the same site. And they had falling costs over time. They also had shrinking construction durations. So South Korea is building nuclear plants in about 4 years. So to zoom in on those costs, what's happening now, as I said, the U.S. didn't build plants for 30 years, but we do have 4 under construction right now, and they're coming in right here. Now that's expensive, but it's not as bad as it was in the 70s or 80s. And these are first of a kind, passively safe, what we call Gen 3 plus plants. And these are the first ones that have been built in the world. So we expect them to come down in cost, but they're already pretty good. And they're going to generate electricity pretty cheaply. But in South Korea, what I'm showing here, these plants actually aren't being built in South Korea. Does anyone know where these plants are being built? UAE, yes. So Korea really wants to become the world leader in exporting nuclear reactor technology. So they're building their first plants outside of their border in the United Arab Emirates. They're building 4 these advanced Gen 3 plus plants. And they're coming in right around here, about $23.90, $100 per kilowatt. And that's very cheap. Now, it's particularly cheap because the UAE doesn't have any nuclear power right now. They're a new nuclear country. And so to set up the entire industry from scratch, to build in a different country, this is pretty incredible. And this is what we'd like to see more of, particularly for countries that are rapidly increasing their consumption of electricity. They need these big, large-scale plants, and it would be amazing if they were all low-carbon generation technologies. So if Korea is successful here, we'd like to see this model in other countries, especially ones that are rapidly industrializing and have that large growth in electricity. But coming back to these really expensive reactors in the US, they're actually not that bad because most of these are still operating today. And they're actually generating really cheap electricity. So this is a chart of real generating costs across the US for actual plants, how much it costs them to generate electricity. And nuclear comes in here at about $25 a megawatt hour, or 2.5 cents per kilowatt hour. You might recognize that number from your utility bill. But we'll just say it's 2.5. Fossil steam, coal or natural gas is more closer to 3.7. Hydro is very cheap because most hydro plants were built 100 years ago. And they're very cheap. And then gas turbines are pretty high too. So even though those plants were way over budget, very expensive to build, they're generating cheap electricity today, and that's because they generate 24/7, huge amounts of power for 40, going on 60, maybe 80 years. So these are really good investments for the long term. But why is that not so great? So, because of that high upfront cost, utilities don't want to build them as much anymore. So let's look at sort of the future costs really quick. I'm going to speed through these. This is from EIA looking at how much will it cost to generate electricity from a new power plant that starts up in 2022. Nuclear's here. They call it advanced nuclear. It's not that advanced. It's those AP1000s that we're building right now in the US. So it's about here. Here are the intermittent renewables, onshore solar, offshore wind, solar thermal. And they have a big spread because they're very geographic and resource dependent. Then you have hydro, biomass, and geothermal. And, nuclear is in there with them, so that's good. But the big thing that we're trying to compete with, especially going forward, is going to be combined cycle gas turbines, so natural gas. So that's the cost that they're projecting of natural gas in 2022. So that's sort of what we compete with. And some of these, nuclear comes pretty close. But ultimately, we'd like it to be cheaper. And we do think that the advanced reactors are going to come in here at about 40 or 50, so below the cost of natural gas going forward. Okay, but the big thing, and Arma mentioned this a lot, is that we need baseload power and dispatchable power, and our options are pretty limited to geothermal, hydro, biomass, and nuclear, and all of these have different kinds of problems, which we can talk more about, but nuclear is one of the only ways that you can get baseload low-carbon power, except hydro. So, limited options. So just in conclusion, we need a mix particularly from what we've seen in recent history. When nuclear plants shut down, they're replaced by fossil fuels. They're not replaced by renewables, and that's a lose for the climate. So particularly, this is a chart for Germany, and we think of Germany as being a leader in renewable energy. Germany has actually built more coal plants, new coal plants in the last 10 years than the rest of the EU combined. And that's because they're shutting down their nuclear, but they still need baseload, especially to offset all of their intermittent renewable energy. They also import and export a lot with their neighbors to balance their grid. So it's not so clean, and we've seen a similar thing in California. When San Onofre closed in California, the state's power sector emissions jumped 50% in 1 year. That's not the direction we want to be going in if we're concerned about climate change. Similar story in New England with the recent closures, and in Japan at a very large scale. So studies that look at different types of mixes find that ones that have a lot of nuclear are cheaper, they're more feasible, and this is going to be a hard task to mitigate climate change and stop sort of catastrophic risks. So we want to keep all our options on the table, and we want to do what's cheapest, easiest, least painful for the people and the economy. So, okay, cost is still a big burden. Okay, so I'll just say that, as Armin mentioned, we want to go smaller and we want to go factory produced. That's the big thing. So there's a company in the U.S. called NuScale. They just submitted their license last year, and they're building really tiny reactors, 45 megawatts. That's unheard of small in the nuclear industry, but they're going to build them like cars or airplanes on a factory assembly line and then ship them to the site. And they're planning to build their first plant in Idaho to supply electricity for Salt Lake City and to replace some of the coal plants that they want to phase out there. So that's a great model. That's what we want to see more of in the U.S. All right. And as Armin mentioned, there's these Gen 4 designs: molten salt, thorium, metal-cooled, breeders, burners, floaters, all sorts of different designs that we can talk more about. They're much safer, they're meltdown-proof. Most of them are doing modular fabrication. They have much higher thermal efficiency, and most of them are going to be radically cheaper, and I do want to make this point. It seems counterintuitive that if something was much, much safer, it'd also be much, much cheaper, but that's how the physics of nuclear reactors work out. It turns out, if you move away from light water reactors, it becomes much easier to have passive intrinsic safety, and it also cuts down a lot of your costs because you have less steel, because you're not pressurizing, you have less concrete because you have a smaller footprint, you're burning more of the fuel, so you don't have to do so many refueling outages. A lot of these they produce much less waste. A lot of them can use recycled fuel or actually burn waste as fuel. They're much more proliferation resistant. A lot of different business models. I mentioned doing floating reactors, doing build, own, operate, remove model, which is selling a nuclear reactor like a battery, where you send it to a site, maybe in sub-Saharan Africa. They operate it for 10 or 20 years, and then when it's done, you bring it back to a central reprocessing facility, maybe in the U.S., so that cuts out that proliferation risk. And lastly, there's a growing industry. There's 50 startups in the U.S. working on all sorts of different advanced reactor designs. Faces you recognize like Bill Gates, but then a lot of young engineers who are really motivated by climate change to solve this problem, and they think that nuclear is the best solution, and I hope I've convinced you that it is. Thank you.